Okay, another colligative property we want to look at when we make a solution. Making a solution will cause boiling point of a solvent to go up, called boiling point elevation. It will also cause the freezing point of a solution to go down, or freezing point depression. Now, freezing point depression is why salt is put on the road when there are expected icy conditions, because adding the solute salt will cause the freezing point of the water to be depressed, to go down, and that means it's less likely for the water to freeze on the road. So under certain conditions, you can just put a little salt or a little salt water on the road, and that'll help cause the road to stay clear of ice. Now, that only works within a certain range of temperatures. If you go further north, when I lived in Wisconsin, it would get too cold for adding salt to work in terms of causing ice not to form on the road. So for parts of the winter, they would just put sand down on top of the ice to give you a little bit of traction, and you just have to wait for temperatures to rise for the ice to melt. Now, for boiling point elevation and for freezing point depression, there's an equation that's going to relate how much the temperature changes. So a change in temperature of the boiling point. And again, watch that delta. That means it's a change in temperature. It's not the actual temperature. It'll be a change from whatever the boiling point of the pure solvent would be. The change in temperature of the boiling point is going to be equal to a constant. So there's a boiling point elevation constant for each particular solvent, multiplied by the concentration. And concentration is going to be in molality for both of these colligative properties, for boiling point elevation and for freezing point depression. Now, in this case, if we know the constant, right, that's a constant, it's always going to be the same. There's really just two variables here, fairly similar to what we saw for Henry's law. Right? Once we know the constant, if we multiply by concentration in the right set of units, we'll know how much the temperature changed. If we know how much the temperature changes and we know the constant, we can figure out what the concentration of that solution is. Similar equation for freezing point. In fact, the only difference is the subscripts there for freezing point instead of boiling point. Change in temperature of the freezing point is equal to the constant for freezing point depression times the molality. Okay, now depression, this is going down, so these temperatures are going to get lower. Right? Often you'll see this constant as a negative number, meaning this temperature change is going lower, going negative. Although, since some of you may be looking at other videos online or reading other textbooks, this isn't always negative. The freezing point depression constant isn't always listed as negative. In some cases, it's a positive number, and it's just understood that it's going down. So be careful about that if you look outside of just these videos for information. Okay, let's look at a couple problems. We want to calculate the freezing and boiling points for a 0.22 molal glycerol solution in ethanol. So we've got the molality, concentration of the solution right there. Here in parentheses, we're given the boiling point elevation constant, freezing point depression constant. We're also given the freezing point there and the boiling point of the pure material because, again, this is comparative. We're going to calculate how much those change, but we'll need to either add or subtract that amount to calculate the actual boiling point or freezing point of the solution. So let's start with boiling point. How much the temperature of the boiling point changes is going to be equal to the constant for boiling point elevation times the molality of the solution. We're given both of those numbers. The constant is 1.22 3C per molal. We're given that the solution has a concentration of 0.22 molals. We multiply those together. And we get a change of 0.2684 degrees Celsius. And again, we've got to be careful. That's how much the temperature changes. That is not the actual temperature. So the new boiling point would be adding that change to the existing boiling point. So if we took 78.4 provided in the problem, add 0.2684, right, that would be 78.6684. Now, based on significant figures, right, we're going to have to stop at the tenths place in our answer, since that's where our data stops there in the initial temperature. So we'd want to round this to 78.7 degrees C. That is the new boiling point of this solution. We can do something very similar for a freezing point. So we take the change in temperature of the freezing point. That will be the result of the constant for freezing point depression times the molality. The constant here is negative 1.99 degrees C per molal. Again, the concentration of the solution is 0.22. Multiply these together, and we get a change of 0.4378 degrees Celsius. Now again, this is a change, although that is negative. Don't forget the negative there. So we're going to subtract this from the actual freezing point of the pure material. So the new freezing point would be negative 114.6 degrees Celsius minus 0.4378 degrees Celsius. So that comes out to be 115. So negative 115.0378. Now again, we're limited to the tenths place, so we would want to round that to just negative 115.0 degrees Celsius. That would be the new freezing point of this particular solution. Okay. Now, second problem, we're asked to solve for the freezing point of a solution that boils at 105 degrees Celsius. So that's just a little bit different set of information. But again, there's only two variables in the equation. In this case, we're given enough information to find delta T. When we plug that in, we can solve for the molality of the solution. So since this is an aqueous solution, that means it's water. The new boiling point is 105 degrees C. The normal boiling point of pure water is 100 degrees C. 5 degrees C is how much the boiling point changed. Okay. So if we have a numerical value for delta T, we can use our equation to solve for the molality. So we know that the change in temperature of the boiling point is equal to the constant times the molality. If I just divide through by the constant, that would be the change in temperature of the boiling point divided by the constant is equal to molality. Plugging those in, 5.0 degrees C for the change in temperature, 0.5121 degrees C per molal for the constant. Degrees C is going to cancel out there. Molality units are going to come back to the top of that equation. 5 divided by 0.5121 gives us a concentration of 9.764 molals for that solution. Now, once we know the concentration, we can actually address what's asked here in the question, which is what is the freezing point? Because we have the concentration and we have the constant, that will allow us to calculate the change in temperature for the freezing point. So if let's do the equation here, just so we start remembering that equation. I plug in the constant, minus 1.86, multiply by this molality we just determined in the first part of the calculation, and molality is going to cancel out there. We'll be left with degrees Celsius. So negative 1.86 times 9.764 gives us a value of negative 18.16 degrees Celsius. Now, that's the change in temperature, but in this case, since it's an aqueous solution, the initial freezing point was 0. And so if we take 0 degrees C and we subtract 18.16 degrees C, we get negative 18.16 degrees C. Although if we look back, that constant is only 3 sig figs. So our answer should also be limited to 3 sig figs. So let's round our final answer to minus 18.2 degrees Celsius.